We spent a lot of time talking about the wave-like nature of light. But there's another side to the story that we really haven't touched upon, and that's the particle nature of light. Light behaves like both a wave and a particle. To understand where this idea comes from, and this is kind of outside of the scope of AP chemistry, but it's helpful to know as a backstory. The first term that we're going to talk about here is a black body. A black body is just simply something in physics, like the sun, that absorbs and then re-emits essentially all types of lights. And a perfect black body is not necessarily the sun, but we use the sun as a model for this type of behavior. There was a situation in which physicists were stuck on this ultraviolet catastrophe. And what does that mean? Well, the equations that they had at the time to describe the wave-like nature of light predicted that a black body such as the sun should be emitting more and more light towards the ultraviolet region as we get the wavelength of light to decrease. But experiments actually proved otherwise. It proved that a black body such as the sun actually releases its light as part of a spectrum of colors that doesn't really spiral out of control in the ultraviolet region. So experiments actually predicted at that time that when you heat or you have a black body at a certain temperature, it releases a characteristic blend of colors that can't really be predicted by classical physics. So we needed another model to describe the behavior of light that wasn't a continuous wave. Along came Planck, and along came this idea that light can only exist and be re-emitted in discrete packets or quantities. Quanta. Light is quantized. There seems to be some smallest part of light that can be re-emitted that is not a continuous wave, like we said light behaves like before. Light behaves like a massless particle. The photoelectric effect was an experiment that further validated this idea. And the observations that were very important were these: that long wavelengths of light didn't cause the effect to happen at all. It didn't matter if we shined that long wavelength of light on the surface of the metal for a very long period of time. We didn't see any electrons being released by the metal. That's what the photoelectric effect is. It's when electrons get kicked out of a metallic surface by light. There seemed to be some kind of a threshold frequency that when we reached that threshold, step on a ladder, that threshold frequency, that all of a sudden we started to see electrons getting released. And even furthermore, if we simply shortened the wavelength and made the frequency higher, we were kicking electrons out with more energy. So this helped to solidify the idea that light not only behaves like a wave with a frequency and a wavelength, it also occurs in very tiny, discrete packets called photons. There's a website that I have posted on Canvas that further illustrates this experiment, but again, the details about the photoelectric effect are kind of outside of the scope of what we need to know here in AP Chemistry. The most important idea that came about from Planck's work with Einstein is the fact that energy in the form of light travels in discrete packets called photons. A single photon can be described by Planck's equation. Energy is equal to Planck's constant times the frequency of light, where Planck's constant is 6.626 times 10 to the negative 34th joules times seconds. The key here is that the energy described by this equation is the energy of one single photon, or smallest particle of light, at that frequency. So to practice using Planck's equation, I'd like you to try problems A, B, and C from this problem set. Pause the video take a few minutes, and then we'll come back and review the answers. For letter A, we're simply taking Planck's constant and we're using it in Planck's equation, multiplying it by the frequency to determine the overall number of joules, which are a unit of energy, contained within one single photon. And that comes out to be 3.11 times 10 to the negative 19th joules per one photon. Now, the next follow-up question is, if we know that a pulse of energy contains 5 times 10 to the 17th photons of that type of radiation, well, what is the total energy contained within that pulse? First thing I can do is I can use this information that I calculated above here in letter A as a conversion factor. We know that 3.11 times 10 to the negative 19th joules are in one photon. So therefore, if I fired off 5 times 10 to the 17th photons, and I multiply it by 3.1 times 10 to the negative 19th joules, well, I know that's the energy in one photon, and that works as a conversion factor to give me 0.16 joules. And for letter C, I can work the reverse way. If I know the energy contained within a single pulse, and I know the energy that's contained within a single photon, I can use that as a conversion factor again to find out that a single pulse of energy with this number of joules would contain 4.2 times 10 to the 16th photons. A photon is it's the tiniest discrete packet of energy at that particular frequency. And a photon is a particle, but it doesn't have mass. That's a strange thing, right? It's a particle, it's a thing, but it does not have mass. 6.13 and 6.14, we have some conceptual questions to kind of wrap up the properties of light. Take a moment, see if you can answer these questions, and we'll quickly go over the answers here. In 6.13, we're actually answering some conceptual true-false questions about light. Letter A is true, letter B is false, letter C is false, and letter D is false. For 6.14, letter A is false, letter B is true, letter C is false, and letter D is false. Here's some more conceptual questions for you to try. Pause the video, take a moment to try these, and we'll quickly go over the answers. Like we stated earlier, you should be able to order electromagnetic radiation in order of increasing wavelength. So the order that I would have here is gamma rays are less than yellow light, which are less than red light, which are less than FM radio, and AM radio has the longest wavelength. For 6.17, letter A, the frequency of radiation that has a wavelength of 10 micrometers, I would simply just substitute that into the speed of light equation. C equals lambda nu, solve for nu, and my answer comes out to be 2.998 times 10 to the 13th inverse seconds or hertz. Letter B, I'm solving for wavelength. Substitute into my equation, 5.45 times 10 to the negative 7th meters. For letter C, letter B falls within the visible range. And for letter D, I would simply use the speed of light as a conversion factor to solve for the distance, which would come out to be 1.5 times 10 to the 4th meters. We're going to move on in the next video to the properties of electrons as waves, and that should take us to the end of our discussion of light.